The installation involved tapping off of existing switchgear using a 500 AWG conductor. This conductor feeds a 400 amp service disconnect. A grounding electrode conductor, or GEC, runs with the service conductors from the switchgear to the new disconnect. The load side of the 400 amp service disconnect is equipped with twin lugs. These lugs feed two additional feeder disconnects. Firstly, there is a 200 amp disconnect that utilizes 3/0 AWG conductors. Secondly, there is a 100 amp disconnect utilizing 3 AWG conductors. The installation complies with National Electrical Code, or NEC, Article 240.21 bone. This section of the code addresses the protection of tap conductors. Article 240.21 bone specifically covers tap conductors not over 10 feet long. The conditions for this exception are as follows. 1. The tap conductor's ampacity is not less than the combined calculated loads on the circuits supplied by the tap conductors, and not less than the rating of the overcurrent protective device at the termination of the tap conductors. 2. The tap conductors terminate in a single circuit breaker or a single set of fuses that will limit the load to the ampacity of the tap conductors. 3. The tap conductors are enclosed in a raceway from the tap to the overcurrent device. Now, to delve a little deeper into the specifics of 240.21 bone, it's crucial to understand each component's role in ensuring a safe and compliant installation. 500 AWG conductor, serving as the tap off the switchgear bus, needs to have an ampacity sufficient to handle the total load it supplies. This ampacity must be equal to or greater than the combined loads of the 200 amp and 100 amp disconnects it feeds downstream. The 400 amp service disconnect acts as the primary overcurrent protection device for the entire tap system. It safeguards the 500 AWG conductor from overloads and short circuits, preventing potential damage to the equipment and minimizing the risk of electrical hazards. The grounding electrode conductor, or GEC, plays a critical role in providing a low impedance path for fault currents to return to the source. This path facilitates the rapid tripping of overcurrent devices such as circuit breakers or fuses in the event of a ground fault, thereby reducing the risk of electrical shock and equipment damage. The twin lugs on the load side of the 400 amp service disconnect are designed to accommodate the two separate feeder disconnects, namely the 200 amp and 100 amp units. These lugs must be properly sized and rated to ensure a secure and reliable connection for the conductors feeding the downstream disconnects. The 200 amp disconnect, utilizing 3/0 AWG conductors, serves as the overcurrent protection device for the feeder circuit supplying a specific portion of the load. The 3/0 AWG conductors must have an ampacity sufficient to handle the load they supply, as well as be adequately protected by the 200 amp disconnect. Similarly, the 100 amp disconnect, utilizing 3 AWG conductors, provides overcurrent protection for another feeder circuit. The 3 AWG conductors must also be sized appropriately for the load they carry and be protected by the 100 amp disconnect. MON meters were installed for metering purposes due to space limitations, preventing the installation of traditional service metering equipment. These meters allow for accurate monitoring of energy consumption, enabling efficient energy management and billing. The NEC compliance, particularly with Article 240.21 bone, ensures that the installation adheres to established safety standards and best practices. This compliance minimizes the risk of electrical hazards and ensures the long-term reliability of the system. In the context of electrical installations, especially in older buildings or confined spaces, innovative solutions are often necessary to overcome physical limitations and meet the demands of modern equipment. The observed installation demonstrates how careful planning, precise execution, and adherence to established codes and standards can result in a safe, reliable, and efficient electrical system, even under challenging circumstances. In this particular case, the limited space available required careful consideration of conductor routing, equipment placement, and conduit bending techniques. The contractor's skill in bending the conduit to navigate the tight space is commendable, as it demonstrates their expertise in overcoming physical constraints while maintaining code compliance and safety standards. The use of Amon meters instead of traditional service metering equipment further highlights the innovative approach taken to address the space limitations. These meters provide accurate energy monitoring without requiring the same amount of physical space as traditional metering setups. To further elaborate on the NEC requirements and the specific components involved, let's consider a hypothetical scenario. Imagine a situation where the calculated load on the 200 amp disconnect is 180 amps and the calculated load on the 100 amp disconnect is 90 amps. In this case, the 500 AWG tap conductor must have an ampacity of at least 180 amps plus 90 amps, which equals 270 amps. According to NEC Table 310.16, a 500 AWG copper conductor with a 75 degrees Celsius insulation rating has an ampacity of 380 amps, which is more than sufficient to handle the combined loads of the two downstream disconnects. It's important to note that the ampacity of the tap conductor must also be equal to or greater than the rating of the overcurrent protective device at the termination of the tap conductors. In this case, the 400 amp service disconnect serves as the overcurrent protection device for the tap conductors, and the 500 AWG conductor's ampacity of 380 amps is adequate for this purpose. Additionally, the tap conductors must terminate in a single circuit breaker or a single set of fuses that will limit the load to the ampacity of the tap conductors. The 200 amp and 100 amp disconnects fulfill this requirement by providing overcurrent protection for their respective feeder circuits. Furthermore, the tap conductors must be enclosed in a raceway from the tap to the overcurrent device. This raceway provides physical protection for the conductors and helps to prevent accidental damage or contact with other objects. In summary, the observed installation demonstrates a well-designed and executed electrical service upgrade that addresses the challenges of limited space and the need for increased electrical capacity. The use of a tap-off existing switchgear, along with careful consideration of conductor sizing, overcurrent protection, and grounding, ensures a safe, reliable, and code-compliant installation. The innovative approach taken by the engineer and contractor showcases their expertise in electrical design and installation practices. Let's delve deeper into the specifics of conductor ampacity and overcurrent protection to further illustrate the principles at play in this installation. According to NEC Table 310.16, the ampacity of a conductor depends on several factors, including the conductor material, insulation type, and ambient temperature. For example, a 3/0 AWG copper conductor with a THHN insulation rating has an ampacity of 200 amps when installed in a raceway or cable and used in an ambient temperature of 30 degrees Celsius. Similarly, a 3 AWG copper conductor with a THHN insulation rating has an ampacity of 85 amps under the same conditions. It's important to note that these ampacity values are based on specific assumptions about the installation conditions. If the ambient temperature is higher than 30 degrees Celsius, or if the conductors are installed in a manner that reduces their ability to dissipate heat, then the ampacity must be derated accordingly. Derating factors are provided in NEC Table 310.15b2 and 310.15b3 respectively. In addition to conductor ampacity, overcurrent protection is another critical aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from overloads and short circuits. When an overcurrent occurs, the protective device will trip or blow, interrupting the flow of current and preventing damage to the electrical system. The NEC specifies the maximum allowable overcurrent protection for different types of conductors and equipment. In general, the overcurrent protection device should have a rating that is equal to or less than the ampacity of the conductor it is protecting. However, there are some exceptions to this rule. For example, NEC Section 240.4b allows for the use of the next highest standard overcurrent device rating in certain situations, provided that the conductor is protected against short circuits and ground faults. In the observed installation, the 200 amp disconnect protects the 3/0 AWG conductors feeding the downstream load, while the 100 amp disconnect protects the 3 AWG conductors. These overcurrent protection devices are sized appropriately to protect the conductors from overloads and short circuits, while also allowing for the safe and reliable operation of the connected equipment. Now let's consider the grounding electrode conductor, or GEC, in more detail. The GEC is a critical component of the grounding system, which provides a low impedance path for fault currents to return to the source. This path facilitates the rapid tripping of overcurrent devices in the event of a ground fault, thereby reducing the risk of electrical shock and equipment damage. The size of the GEC is determined by NEC Table 250.66, which is based on the size of the service entrance conductors. For example, if the service entrance conductors are 500 AWG copper, then the GEC must be at least 1/0 AWG copper. The GEC must be connected to a grounding electrode, which is typically a ground rod, ground plate, or metal water pipe. The grounding electrode provides a direct connection to the earth, which helps to stabilize the voltage of the electrical system and provide a reference point for fault currents. In the observed installation, the GEC runs with the service conductors from the switchgear to the new disconnect. This ensures that the grounding system is properly connected and provides effective protection against ground faults. In addition to the GEC, the equipment grounding conductor, or EGC, is another important component of the grounding system. The EGC provides a low impedance path for fault currents to return to the source from the metal enclosures of electrical equipment. This helps to prevent the metal enclosures from becoming energized in the event of a fault, thereby reducing the risk of electrical shock. The size of the EGC is determined by NEC Table 250.122, which is based on the rating of the overcurrent protection device protecting the circuit. For example, if the overcurrent protection device is rated at 200 amps, then the EGC must be at least 6 AWG copper. The EGC must be connected to the metal enclosures of all electrical equipment, such as junction boxes, panel boards, and motor housings. This ensures that the equipment is properly grounded and protected against electrical shock. In summary, the grounding system plays a critical role in ensuring the safety and reliability of electrical installations. The GEC and EGC provide low impedance paths for fault currents to return to the source, which helps to prevent electrical shock and equipment damage. The NEC provides detailed requirements for the design and installation of grounding systems, which must be followed to ensure compliance and safety. Immon meters are used for metering purposes, particularly in situations where space is limited. These meters are designed to accurately measure energy consumption without requiring the same amount of physical space as traditional metering equipment. Immon meters typically use current transformers, or CTs, to measure the current flowing through the conductors. The CT are installed around the conductors and produce a small current that is proportional to the current flowing through the conductor. The meter then uses this current to calculate the energy consumption. Immon meters can be used to measure a variety of electrical parameters, such as voltage, current, power, and energy. They can also be used to monitor other parameters, such as temperature and humidity. Immon meters are commonly used in commercial and industrial applications, where accurate energy monitoring is essential for energy management and billing purposes. They are also used in residential applications, where they can help homeowners to track their energy consumption and identify opportunities to save energy. The use of Immon meters in the observed installation demonstrates the innovative approach taken to address the space limitations. These meters provide accurate energy monitoring without requiring the same amount of physical space as traditional metering setups. To provide a more comprehensive understanding of the NEC requirements for tap conductors, let's consider some additional scenarios and examples. Suppose that the tap conductors are longer than 10 feet, but not more than 25 feet. In this case, NEC section 240.21b2 applies. This section allows for tap conductors up to 25 feet long, provided that certain conditions are met. Firstly, the tap conductor's ampacity must be at least 1/3 of the rating of the overcurrent device protecting the feeder. Secondly, the tap conductors must terminate in a circuit breaker or set of fuses that will limit the load to the ampacity of the tap conductors. Thirdly, the tap conductors must be protected from physical damage. In another scenario, suppose that the tap conductors are supplying a transformer. In this case, NEC section 240.21c applies. This section provides specific requirements for tap conductors supplying transformers, which are designed to protect the transformer from overloads and short circuits. The requirements for tap conductors supplying transformers depend on the size of the transformer and the length of the tap conductors. In general, the tap conductors must have an ampacity that is at least 1/3 of the rating of the overcurrent device protecting the feeder, and they must terminate in a circuit breaker or set of fuses that will limit the load to the ampacity of the tap conductors. Additionally, the tap conductors must be protected from physical damage. It's important to note that the NEC requirements for tap conductors can be complex and may vary depending on the specific application. Therefore, it's essential to consult the NEC and other relevant standards to ensure that the installation is compliant and safe. In conclusion, the observed installation demonstrates a well-designed and executed electrical service upgrade that addresses the challenges of limited space and the need for increased electrical capacity. The use of a tap-off existing switchgear, along with careful consideration of conductor sizing, overcurrent protection, and grounding, ensures a safe, reliable, and code-compliant installation. The innovative approach taken by the engineering contractor showcases their expertise in electrical design and installation practices. The contractor's skill in bending the conduit to navigate the tight space is commendable, as it demonstrates their expertise in overcoming physical constraints while maintaining code compliance and safety standards. The use of ERM1 meters instead of traditional service metering equipment further highlights the innovative approach taken to address the space limitations. These meters provide accurate energy monitoring without requiring the same amount of physical space as traditional metering setups. The compliance with NEC Article 240.21 ensures that the installation adheres to established safety standards and best practices. This compliance minimizes the risk of electrical hazards and ensures the long-term reliability of the system. Overall, the observed installation serves as a valuable example of how to overcome challenges and implement innovative solutions in electrical design and installation.